Now that we have bit-level basics covered, this topic covers C's bitwise operators. Operators on integers that deal with the bit patterns in the integers rather than with their numerical values. First, let's talk a bit about why we even care about bit patterns. It's often useful in hardware-oriented design or when memory efficiency is important to work directly with the bits within an integer. For instance, one can use each individual bit of an integer to represent a separate true-false value, and thus get many booleans in one int. Or each bit might be used for a black-white pixel in an all-black-white image. An integer might also be broken up into separate bit fields, groups of bits within the larger integer, with each bit field holding a small value in its own right. A field of 6 bits, for instance, can hold unsigned values from 0 to 63. Configuring hardware tables, as in an MMU, often requires breaking an integer into bit fields. Compression algorithms, making use of every possible bit of compressed storage, often take this a step further, treating an array of integers as a long sequence of bits to hold compressed data, and storing compressed values in as few bits as possible without even caring much where one integer ends and the next begins. The compression algorithms will bridge a bit field across 2 ints by using remaining bits from the first int along with a few bits from the next int to store a value. And we're going to have a lab and some LMQs that may do that sort of thing, in fact. To address individual bits or groups of bits within an integer, we use C's 6 bitwise operators that are illustrated out in the code example. To show how these work, the example code declares ints I and j on lines 4 and 5, initializing them in hexadecimal to contain the bit patterns shown in the comments over here after their declarations. Then on line 9, we use 4 of the bitwise operators in a printf, and we show the results, at least partially, in a table down on the right margin as well. Don't look at the printf output until you've done the questions below. So, the first bitwise operator is I, or it's ampersand, and we have I ampersand j here. This is distinct from the double ampersand operator. Rather than doing an AND operation on the entire values of I and j, it does an individual AND on each pair of bits within I and j, producing an integer result from what is, in effect, 32 individual bit-sized AND operations. The table here shows the details. For each bit pair in I and j, the result, I and j, has a 1 bit only if both the operand bits are 1, and thus their AND would be a 1. But if either operand bit is a 0, then the result is 0. Now, the diagram intentionally leaves off the last 12 bits of the I and j result here. Fill in those last 12 bits to be sure you get the idea. Coming back from a pause, what you should have gotten in there was 0, 0, 0, 0. None of those bit patterns have 2 1s, but then there's a 1 here, 0, 0, 0. And in here we get 0, 0, 0, and a 1 there. Now, the next bitwise operator is single or pipe. This predictably does an OR operation on each bitwise pair, with the result having a 1 bit if either or both of the operand bits is 1, and a 0 bit only if both operand bits are 0. Again, you can see this in the example here. Trace the example to see what I mean, and then fill in the last 12 bits of the I or j result. Coming back from a pause, since 0 or 1 is 1 here, we do 0 or 1 there, and we get a 1. 0, however, ORed with 0 remains 0. 1 or 0 is, 1, and a 1 there. And indeed, in general, any time one or the other or both of the operand bits are 1, we get a 1. But if they're both 0, we get a 0. Thus. Now, the third bitwise operator is up arrow. And this does an exclusive OR on the bit pairs. It produces a 1-bit only if the two operand bits are different, if they are a 0 and a 1, or a 1 and a 0. But if they're a 1 and a 1, it produces a 0. As before, you can trace the result in our diagram here. Anytime we have bits that are the same, 0 and 0 or 1 and 1, we get zeros for the exclusive OR. But when the bits are different, then we get a 1. And as before, please fill in the last 12 bits. Coming back from a pause, what you should have gotten is thus and there. And finally, the last bitwise operation in this printf is tilde. This is unary. It takes only one integer operand. The result is a bit pattern with every bit flipped. And again in the table you can see that we have a bit pattern here that is exactly the opposite of the bits in I. Now, question 4, this one's pretty trivial, but just to see if you're awake, fill in the last 12 bits that would result from the tilde I here. And after a presumably short pause, we're going to have 1100, 0110, and 1010. Now, you can check that the printf output reflects the results of these 4 operands in hex, as I've been putting it here. Here's the output down on line 30. We could have printed the results in decimal, too. They do have a decimal numerical value, but that value is usually uninteresting when we're looking at bitwise operations. It's the bit patterns we're after, and hexadecimal shows those more clearly. So, with those operations in hand, my next question is sort of an interesting thought issue here. There are integer-level Boolean operators, double ampersand and double pipe, and they correspond to the bitwise operators and pipe, but of course they work at the full integer level. Is there a Boolean operator for exclusive OR to go with the bitwise up arrow? There is no double up arrow, but there is an operator you already know that does the same thing. So here's question 5. In the if statement shown here, fill in operator in the space in the transcript such that the entire test will be true only if one subtest or the other subtest is true, but not if both of them are true, or if both of them are false. Coming back from a pause, a not equal operator will accomplish this. Each subtest produces an integer, 1 or 0 result, reflecting its truth or its falsity. And a not equal comparison of those results will be true only if one subtest is true and not the other. Now, one of the most common use of bitwise operators is to set or clear groups of bits within an integer. And such use always involves masks, which are integer values with 1 or more 1 bits, usually in a contiguous group, and 0 bits everywhere else. Lines 11 through 12 down here give an example. Using the mask OX7FO, which has the bit pattern looking like this, with 7 1-bits in a group and the rest 0 bits. Now, if we AND an integer I with this mask, the result bits will have to be 0 wherever the mask has 0 bits, regardless of the bits in I. But where the mask has 1 bits, the result will depend on I's bits. If I has a 0 bit, then the result is still 0, but if I has a 1 bit, then ANDing it with a corresponding 1 bit in the mask produces a 1. We can think of the mask then as indicating which bits to preserve and which to set to 0, at least if we AND it with another integer. Question 6. So what if we OR the mask with an integer like I? What effect does that have? Think it through and frame your answer in terms of what bits the operation preserves and what bits in I it changes. And the answer, after a pause here, is that the OR operation will preserve the bits in I where the mask has zeros, and will set the bits to 1 where the mask has 1s. In this case, the mask indicates which bits to turn on and which to preserve unchanged. So with appropriate masks, we can now switch on or off selected bits within an integer, producing a new bit pattern, which we can assign or print out. But what if I wanted to clear the 7 bits that are 1s in the mask? ANDing preserves those bits, ORing turns them on to 1. How do I make them go to 0? I could, of course, create another mask by flipping those bits to zeros and having all the others be 1s. The hex for that is shown in the transcript, OX, FFFFF, ADF. But writing all those Fs is tedious, and there is another choice. I could clear these 7 bits in the mask, or clear these 7 bits in an integer I using the mask, by keeping the existing mask, but inverting it by the tilde operation. And that's shown here in the printf. Our first 2 operations, ANDing the mask and ORing it, are here, or actually here in the argument list. And the one I'm proposing now is here, I and tilde OX7FO, which will produce a mask with all 1s except for the 7 bits that were 1s and will now be zeros. This AND operation then would have the effect of clearing those 7 bits. It's common style to set up a mask with 1s for what we might call the bits of interest, and then use an OR on the mask to turn those bits of interest on in some other integer, and an AND tilde mask operation to clear them.